I'm all right, yeah.
I'm sorry, was that English? I don't even know what you said.
I'm just expressing my confused state when they say computational problem.
Oh, right.
My brain just.
That's it for you.
Yeah.
You're good.
Go for it.
Okay, so yeah, my project is computational modeling of malposition coronary stents, which is the research that I was doing over the summer. Okay, just some background information of where this project comes from. Some of the most common problems with, just make sure everyone's familiar with stenting. Just it's like a little metal tube that you stick into a blood vessel to keep it open after it's been like blocked off. So the most common complication is in-stent restenosis, which occurs in, 25 to 50%. The different papers cite different numbers, but it's very common after effective stenting a vessel. And the really fatal one would be in-stent thrombosis. That's when blood clots form inside the vessel, and both of them are particularly common complications with stenting. Some previous research indicates that it's triggered by an immune response to the damage to the vessels that these stents can cause, and people have looked into drug-eluting stents to sort of fend off that immune reaction. So if you guys were paying attention yesterday, everolimus is one of the drugs that they use. But what's really not as well understood is the mechanical causes that sort of trigger the biological responses. So that's the point of these experiments. We're trying to find out what mechanically about the stents is causing the restenosis and thrombosis. Okay, malposition. That's one of the mechanical effects that we're looking at. It's basically how you put a stent into a vessel. It's basically like a wire. It's called like a catheter, and you put the stent onto the catheter, and you stick it up through your leg into the blood vessels, and you use a balloon that you inflate with water to open up the stent. But if the balloon doesn't open up all the way, it can the stent can sort of collapse in on itself, and so the struts of the stent are not flush with the outside wall of the vessel that's lumen, which disrupts blood flow through the stent. So that will create variations in a whole bunch of different forces. The wall shear stress, which is basically a frictional force between the blood vessel wall and the shear rate, which is that over time, and the strain rate, which is the rate of deformation of the vessels. So it obviously has a lot of different mechanical effects on the vessels. So we're trying to see if that has a correlation to the biological effects that we're seeing that cause restenosis and thrombosis. And if you look at the picture, you can sort of see. I tried to pick one that had a lot of malposition in it.
Okay, I think we're pretty good on the background. So what do you want to do?
Oh, okay.
No?
Okay, not gonna freak out. Okay, so here's the first step of the experiment. That's OCT, optical coherence tomography. Basically, you take slice pictures of, in this case, the blood vessel, and you use them to reconstruct a computer geometry of the vessel that you can run simulations on. So we get the frames from St. Jude's. So the first thing that we have to do is identify from these pictures that we get. You have to get a mathematical equation that'll represent the structure of the stent. So first thing you got to do, you got to identify all of the struts and where the lumen is. I sort of tried to make a picture. I couldn't open up the MATLAB files on my computer because I didn't have it, so I tried to make a picture of kind of what you're doing. So you have to identify the wall of the lumen and all of the struts. So we're trying to make it like a MATLAB script that will identify all of these things based on previous data. So it'll classify from training data to create a program that will identify all these things. But you also have to check it all by hand because computers make mistakes all the time. If anyone ever told you that computers eliminate human error.
So you want to redraw the vessel wall
with a mathematical equation.
Right.
What is the blue circle?
And then what do you want to do with that equation?
I'll get to that.
Okay. What's the blue circle?
What's the blue circle?
That's kind of trying to make representation of what the existing form of the program does. It sort of like draws around where the lumen is, but you can kind of see it's not like all the way.
So you want something that's gonna not just give you a circle, but give you some sort of
yeah. So we're trying to improve the program to make a better geometry.
Are you looking for a
Geometry
topography or a geometry? Like, are you looking for a shape, or are you looking for the actual surface of that vessel?
I mean, they call it a geometry. It's like a 3D thing that you can use in a.
I guess those are just terms I made up, trying to distinguish between the two.
But yeah, you need the surface. It's not just it's not.
But but what you're doing is looking at a two-dimensional image and trying to basically create a program that will trace the inner walk, that will identify and trace it.
Yeah.
And then using a series of images, you can recreate a 3D
reconstruct the entire thing.
I get it.
It does.
To see stent damage.
Well, after you make that sort of geometry, that's what it's called.
Yeah.
That's what you run the simulations on that. I'll get to that later. And from that, you can see fluctuations in like the other variables I was telling you about, like the wall shear stress and the strain rate and things. And you can see if that correlates to what you're seeing, what the like in vivo effects you're seeing in the rabbit models, which are the exact same stents that are being simulated here. Make
Okay.
sense?
So you're getting the images from patients that have stents.
They're not actual patients, they're rabbits.
But the
rabbit
images are
patients
coming.
that have stents.
You have access to these. They are free. We don't pay for them. They exist.
MIT gets them. They send them to me.
We don't have to wait for
We
them or
don't-
do
we-
anything.
No, we don't have to. I have like
Okay.
100,000 sets of these things.
Awesome. Moving on.
Okay, good for now?
Yeah.
Then this is sort of the CAD element of it. After we make a program that'll identify where everything is, we send it to MIT. They'll send us back the geometry because they have the program that will take our like. Hello, Mr. Burkhardt.
Don't interrupt.
As he interrupts.
Okay, and so they'll send back like a sort of not exactly good geometry because like they'll have it reconstructed like exactly as the stent looks like, and we can't actually do simulations on that because the intersecting geometries, the ANSYS, the CFD solver can't like if you have something like this, you can't. Because basically what it does is it divides it into lots of little pieces and solves a bunch of equations at all those points, so if you have intersections it won't work. So basically what you have to do is you take the incorrect geometry and you like cut off all of the mistakes, and then you have to use the CAD program to fill out the gaps and eliminate the intersections and things like that until you've got something that's workable. That's probably what's going to take the majority of the time. It's really tedious, but it's important because without that you can't do any of the simulations.
So rhinoceros.
What?
Just use rhinoceros.
That's the name of the CAD program. And then you export it to a different CAD program where you have the reconstructed version of the lumen, which is a lot easier to do than the stents. They can do that with angiography. And basically what you do is you cut the stent out of the lumen. So you can do a blood flow simulation. Basically you're running blood through this, so you have the solid body is the
So
stent.
you're running blood through the post-stented blood vessel without the stent.
Yeah, so you need to have the vessel and the stent cut out of the solid vessel, so when you run the blood through, like you're not having blood going through the stent and not through the vessel, you have to go through the vessel and the stent. That's what the Boolean operation is. Basically, you're just cutting it out. Good?
Right now, what I'm seeing is this is purely fact finding. Is that you're not testing anything right now yet, from what I can see, unless it's coming. It is coming. Okay, good.
Okay. So this is all just preliminary to the actual simulation.
Okay.
Here's where it gets a little bit complicated. Okay, so I'm just kind of going to explain how CFD works. It's computational fluid dynamics. It's basically you're taking a geometry and you're trying to simulate the flow through.
Go ahead, sorry.
Go ahead.
Go ahead.
Simulate the flow through the vessel. So how they do that is they take your geometry, you use a program called ANSYS meshing, and you have to make basically a mesh of the thing we just built in the previous slide, and you cut it up into lots of like small pieces, and then it solves a whole bunch of equations at the nodes of all the mesh, and that's how you get all of the variables that I was talking about in the beginning. I don't know if there's calculus involved in that, but basically it's using a guess and check method to solve partial differential equations to find out the shear stress and strain rate and all that stuff. And basically how that works is mass in equals mass out, energy in equals energy out. So, and the residuals are sort of like the difference between one trial and the next trial, so it's guessing a whole bunch of different numbers. So when the residuals get really small, that like this graph will sort of flatline like that, and that's when it stops the simulations, and then it'll spit out a whole bunch of data, and you can make a contour plots and stuff like that. It'll tell you where the stress is elevated, where the strain is elevated, and things like that, and you can compare where that is to what's happening in terms of the restenosis in the rabbits. So you can see if there's like a correlation between the mechanical effects that we're looking at and the biological response.
Can you go back one more time? One more slide. Okay, so as far as materials are concerned here.
I think that's your next, is that your next slide?
Oh,
Yeah.
I'm sorry. Go ahead.
Okay, so yeah, everything can be done on computers.
The simulations, can you do them on? Or do you have to send that back to MIT?
I could send it back to MIT. You could try and do it here also, depending on whether I can get the program. I'm not sure how much it's going to cost. I don't know if I can get a free version. All this stuff I know I can probably get a free version from MIT, if not talk to Mr. Burkhardt about getting all that stuff. But
Are we talking one computer here?
but yeah, I can do all this on my computer. Just in terms of like the overnight simulations, you can't be doing anything else on your computer, so I wouldn't want to do that on my laptop. So we have to use the whole computer for that, but other than that, I can do it all on my laptop.
Makes sense.
Pretend I'm done.
What?
Pretend I'm done.
Okay.
Shut up, buddy. What you are doing? What are you testing? What idea are you testing?
We're trying to see if there's a correlation between stent melon